Welcome to lecture 24. So today we're going to talk about major losses. Major losses are important because it's how a lot of mechanical engineers make money. So major losses are basically a major expense in constructing pipelines, water mains, flow and HVAC. So major losses are, you can see here some sort of really long pipeline or something. Major losses are basically the dominant source of pressure loss and frictional loss that we need to make up for in this flow through the use of pumps. And as a consequence, those pumps take a lot of energy. So one of the biggest expenses for a lot of these utility companies are just basically paying the electricity to power their pumps. So that's why we should care about major losses. Last lecture, we talked in general about internal flows, maybe some important definitions here. So we defined average velocity in an internal flow. So we know that our basically velocity in internal flow has a profile like here. There's a laminar profile, a turbulent profile, but the average velocity is usually what we care about in internal flow. And the average velocity is defined such that to get the mass flow rate or volume flow rate, we can just use the average velocity. We don't have to worry about integrating these profiles every time we do internal flow analysis. So m dot is rho v average A. We define the internal flow Reynolds number based on that average velocity. So it's given there. It's rho vd over mu or vd over nu. And based on that Reynolds number definition, we can determine whether the flow is going to be laminar, transitional, or turbulent. We also talked about entrance length. So an entrance length is, you can imagine when flow sort of enters a pipe, there's going to be a certain amount of time before it's fully developed. Once it's considered fully developed, there's no further evolution of the velocity profile along the pipe. So if you take a slice, the velocity profile, once it's fully developed, it'll be the same velocity profile further down the pipe. And what's happening in that developing region is that the boundary layers are on the top, and you can think of top and bottom of the pipe, but remember, this is a circle, right? This is kind of like an annulus. The boundary layers are kind of growing, and once they connect to each other, the top and bottom boundary layers, we get a fully developed velocity profile. So we have some expressions here. For a laminar flow, that entrance length depends on the Reynolds number, but for a turbulent flow, a good rule of thumb is just 10 diameters from the entrance. And like I said, most engineering flows are turbulent. I didn't have time to show this last time, but I have kind of a visual aid here for entrance length. So this is just like a tube. So assume basically this is fully turbulent flow through this tube. I've indicated roughly what the entrance length on this tube would be. And I've also indicated the developing region and the fully developed region. So the velocity profile, remember, this is u equals u of r. So it's a function of radial position, where we are. In the developing region, u is also a function of x. So as it starts developing, it changes along the length. Once it's fully developed, u is no longer a function of x, it's only a function of r. So you guys can just pass that around. If that helps your kind of understanding of entrance length. Are there any questions on internal flow concepts that we covered last lecture? Okay, internal flows are only going to get more complicated from here. So if there's any questions about this, d is the diameter, right? So d is 2 times big R. So d is the internal diameter of this pipe. That's a very important geometrical quantity there. Okay. Today we're talking about major losses. Okay, so the goal of today's lecture is to be able to calculate pressure drop in a straight circular pipe segment, compute the friction factor for laminar and turbulent pipe flows, and also talk about a bunch of different methods that we can do, that we can use to compute that friction factor. So I'll go over what these are and where you should use them, what you should use for your project, and what you should use for, say, your final exam. So the definition of major losses, these are frictional pressure losses in a straight pipe. So let's draw kind of a straight pipe section. So here's a section of pipe here. The flow is going in like this. The diameter of this, the internal diameter of this pipe is this dimension here. And the length is here. So we're going to basically measure the average pressure at point 1 and point 2. Now, for say a constant flow rate through this pipe, friction causes a loss of energy between points 1 and points 2. That energy loss is basically seen as a pressure drop. Because this flow is incompressible, it's not a slowdown in speed. So for example, the flow is incompressible. So if you have a different volumetric flow rate at point 1 and point 2, there's some sort of volume compression happening, which doesn't occur because this flow is incompressible. So that means that the only way this flow can sort of dissipate energy is by losing pressure, so losing the potential to create flow. So the velocity is the same at points 1 and 2, assuming this is fully developed. The volumetric flow rate is the same between those 2 points. So what we get is a pressure drop along this pipe. So that pressure drop is given as P1 minus P2 delta P. And maybe you guys can help me brainstorm. So what do you think this frictional pressure drop would depend on for a real engineering flow? Viscosity, yeah, that's true. So this would depend on viscosity. So if we have a highly viscous fluid, we should expect a higher frictional pressure drop. What else could it depend on? Yep.
The velocity.
The velocity, right. So the actual pressure drop it experiences will change as a function of the actual speed that it's moving. This is just like friction, like a mechanical friction. You can think of it that way. What else could this depend on? Yep. Density, that's good. That's correct. Any other ideas? Yep. Yeah, how long the pipe is, right? So yeah, if it's longer, you expect that frictional loss to be higher. Anything else? Yep.
Does it depend on, like, is that you said the flow is fully developed, but is it only going to be like the laminar or turbulent, like the boundary layer? Would that, how does that affect?
It depends on whether the flow is laminar or turbulent, definitely. Yeah. If you remember from that video of laminar and turbulent pipe flows, they look quite a bit different. And so we have pretty different methods to characterize the pressure loss, whether or not it's laminar or turbulent. So we have to be able to account for all those turbulent fluctuations. Any other ones? Yes? A diameter, right? Very good. Okay. There's really one more that I can think of. So for a real engineering flow, we're leaving our kind of idealized case. Yep. Volumetric flow rate. So that it does depend on that, but that's kind of tied into velocity. So the flow rate. Yeah. Yep.
The coefficient of friction of the inside of the pipe.
Right. So it should depend on some sort of material properties. Like if we have a pipe with really rough walls, we should expect higher frictional losses. So that's going to be called the roughness. Okay. So now I'll give you the equation. So by the way, this friction factor that we're going to talk about today the form of it can be derived by Buckingham pi theorem by looking at all of these things that we just brainstormed. I'm not going to do that today. So this pressure drop is F, where F is the friction factor, times L over D times rho V average squared over 2. So this is basically what we're going to look at today is the friction factor. and it's named after someone called Darcy. So Darcy friction factor. So the friction factor is really nice because it basically distills all of these things we talked about into one factor. So for a general design problem, you already know, say roughly the length of your pipe, the diameter of the pipe, the flow rate and the fluid properties. So what we have to do now is be able to compute the pressure drop in that pipe, and we need the friction factor in order to do that. So basically the rest of this lecture is going to really focus around calculating that friction factor, because once we have the friction factor, this equation is fairly easy to use. Okay. Okay, so let's talk about how to find F. First way, and I would say the easiest way, is we can use this equation. So F equals 64 over the Reynolds number based on diameter. So F is dimensionless, right? Let's just talk through the dimensions of this pressure drop. So this pressure drop is in units of pascals. So F is dimensionless. L over D is dimensionless because those meters cancel out. And this rho v average squared is kind of like a dynamic pressure. So that's the units of pressure. So both of these quantities are dimensionless, so we get pressure out. So F is 64 over Reynolds number based on diameter. Again, both of those are dimensionless. This is quite a nice equation because basically all the variables except viscosity are included. We already know that in the top equation. The problem is this is only for laminar flows. So if you recall last time we talked about the criteria based on that Reynolds number of whether or not it will be laminar or turbulent. So if you find out that you have a laminar flow, that's how you can calculate that friction factor. So quite easy. As always with turbulent flows, everything is more complicated. So for turbulent pipe flows, the kind of the gold standard in terms of accuracy is called the Colebrook equation. And that's for turbulent pipe flow only. Okay, so here's what the Colebrook equation is. It's 1 over the square root of F is negative 2.0 log base 10 epsilon over D, or 3.7, plus 2.51 for Reynolds number D square root F. So this is the Colebrook equation. So epsilon here is the mean surface roughness. And that has units of meters. Well, it has units of length. It's usually given in millimeters, but it has units of length. And this parameter here, epsilon over D, I'm going to do that in green. So epsilon over D, that's called the relative roughness. And that is unitless. Yeah, so this equation is quite famous in pipe flows, the Colebrook equation. It includes basically everything we talked about. So the effective viscosity, for example, and density, velocity, diameter, all of that is included in the Reynolds number. The effective length is included, say, up here. After we determine our friction factor, we use length there. Just for consistency, I'm going to make these both red so we can see. Now, there's a problem with the Colebrook equation. Um, that is, I guess if you talk to anyone who took fluids one, they'll probably remember this problem, but what's the problem with the Colebrook equation right here? It's an implicit equation, so we can't say F directly out of this equation. Um, so we have a few methods to get around this because we need to get F out of this equation. And that is, there are many different approximations in pipe flows for this friction factor, and they're all basically formed around approximating this Colebrook equation. So in this course, we're going to use one approximate equation for that, just for consistency. I will do, okay, so maybe I'll give you the algorithm for how we actually solve the Colebrook equation first before we talk about how we approximate it. So the problem is that this equation is implicit in F. So how to solve this? So the first step is we guess F. Second step is we compute the right-hand side. So the right-hand side of this equation, if you know F is just a number, so we can basically evaluate what that right-hand side is after having guessed F. Now, we know what the right-hand side is, that's just a number. We can find F using the left-hand side. From the left-hand side, F equals 1 over the right-hand side squared. Once we have that new value of F, we want to go back to step 2 with our new F. And so on. So you can iterate this as many times as you like. The nice thing is this generally converges fast. But here's the algorithm, and I'll do an example as well. So that's one way to compute F, and it's the most accurate way to compute F. The second way that I'm including to compute F is I'm including this because it's more classic. So you wouldn't be doing fluids 1 if you didn't talk about the Moody chart, basically. So the Moody chart is the Colebrook equation in chart form. So the annoying part of this equation was that it was developed at a time when people didn't even have calculators that could do like the log base 10 operation. So very quickly, someone wanted to make a chart form of this, so people could just look it up using the chart. So I will do an example later where I'm going to talk about how to use this chart. But basically, this chart is, if you know everything in the Colebrook equation except F, you can use this chart. Okay, the fourth method is an approximation of the Colebrook equation called the Holland equation. The Holland equation is very nice because it says 1 over the square root F equals negative 1.8 log 10. So I'm writing the 10 in the base 10 of log because sometimes it's unclear. People will use the natural log interchangeably with log. So that's why I'm leaving that. For example, some people use ln and log interchangeably, but in this case, it is the base 10 log. So make sure when you're doing this in your calculator or whatever software you use to do this, you're getting the base 10 log. Because if you use the natural log here, you won't get the right answer. So this is the Holland equation. And the Holland equation is very nice because, well, first off, it's very nice for us because it's it's explicit in f. F only appears once and it appears on the left-hand side. So we don't have to do any iterations with the Holland equation. The second reason that it's nice is it's within 2% accuracy of the Colebrook equation. So it's good enough for hand calculations. We don't have to do any iterations when we do calculations by hand. Are there any questions about these methods yet? I'm going to go through an example where it's going to be a little bit more clear of how do you do this. Yep.
I know we said round number for the other one was like completely different things, but is there any correlation to like the skin coefficient for laminar flow? Because isn't it like
Yes.
6.4 divided by the round number, which is pretty similar, like 64 divided by.
It's a good observation. So I think your question was basically, is there a relationship here between the skin friction coefficient that we could get from, say, the wall shear stress and this friction factor, right? So that's actually where this analytical form of the Reynolds of the friction factor for laminar pipe flows comes from. So that 64 over RED comes from, we can analytically get the skin friction coefficient for sort of the skin friction coefficient for a pipe. That's where that comes from. The other thing that I want to point out is the surface roughness part doesn't actually appear in the laminar pipe flow friction factor. That's because for most engineering sort of level of surface roughnesses, for laminar pipe flows, it really doesn't matter. Laminar flows are so viscous and stable. The surface roughness, assuming you don't have an insanely rough pipe, doesn't really matter for a laminar pipe flow. For turbulent pipe flows, because every single little thing in a turbulent flow will cause instability, that's why we care about surface roughness now for turbulent pipe flows. Any other questions about this? Yep.
By just looking at the surface roughness thing, because could you also tell if someone gave you a roughness value, if it was the F.
Yep.
If someone gave you a value, could you from that just say if the flow was laminar or turbulent?
No, I don't think you could. We'll see on the Moody. So the question was, could you just roughly guesstimate? Somebody said F is like say 0.015. Oh, that's usually for laminar turbulent. Maybe let's do a little spoiler. So I'll go to the Moody chart to show you this. So the left-hand side of this Moody chart is the friction factor. I'm going to talk about how to use this chart. But so the left-hand side of this chart is the friction factor. So for the laminar flow, you get that linear 64 of the Reynolds number. So you can see you actually get the same friction factor. You can have a laminar and turbulent pipe flow with the same friction factor, but they look very different. So these blue lines are your kind of Moody chart lines. So that will make more sense after I do the next example. Any other questions? Okay, I'm going to copy this just because I need it. That chart is also posted on Learn. It's a scan from one of the course textbooks. So let me give a recommendation of when to use which method. So if you're doing hand calcs, like for example, an exam, you first check the Reynolds number based on diameter. And then based on that, you're going to use the F is 64 over the Reynolds number or Holland equation. So there's a lot of opportunity for calculator errors when you're iterating the Colebrook equation. There's an insane amount of opportunity for calculator errors. So let's just use the Holland equation on exams. So it's only one calculation step. So again, it's pretty accurate. It's within 2%. So that's okay for hand calcs. But when you have access to a computer, should again check the Reynolds number first, and then use 64 over Reynolds number. Again, that's only for turbulent flows. That's why we're checking the Reynolds number, or the Colebrook equation. So, for example, on your project, you should be using the Colebrook equation, so you guys learn how to do those iterations. So you'll notice I haven't actually recommended using the Moody chart here, and that's because I think basically in this day and age, you all have access to calculators that can do log and do things to the power of, say, 1.11, etc. So we'll just use I think it's almost harder to use the Moody chart than it is just to run this through your calculator. So the Moody chart I'm going to show you, I'll include it on your exam, but I'll ask you to use the Holland equation on your exam. So you could use it to check your Holland equation calculations if you have time. Okay. So let's just summarize these methods. So for laminar, so based on our Reynolds number, we determine whether the flow is laminar, transitional, or turbulent. So this table is titled How to Get the Friction Factor. Okay, so if you use F is 64 over Reynolds number, that's only valid for laminar flows. The Moody chart, as I showed, the Moody chart has the friction factor for laminar and turbulent flows on it. So you can use that in either case. By the way, this is just these are not my recommendations. This is just what's actually valid. What's valid. The Colebrook equation is only valid for turbulent flows. That's the same for the Holland equation. So if you look at this table, I basically haven't given you a method to calculate friction factor for transitional flows. That's because by far, almost all the flows we deal with in engineering are fully turbulent. If you're dealing with transitional flows, you'll have to look up some specialized correlations or things like that. So I'm not going to ask you to compute the friction factor for a transitional flow in this course. So if I go back to the Moody chart, the Moody chart doesn't even give you the friction factor for transitional flows. It's just kind of this big blurry question mark area there. Okay. Let's do an example here. So the example is calculate major loss, which again, the major loss is the pressure drop in a straight pipe section. In a 30-meter long NPS 12 schedule 80 steel pipe with water so rho is that. I'm also going to give you new flowing at 0.1 cubic meters per second. So this is kind of motivated by what you're expected to do on your project and also the real world where you're not given the internal diameter of the pipe, you're given, say, a standard pipe size and a wall thickness here. So I'll explain what those mean. So this question is basically going to take the rest of the lecture because I'm going to do the friction factors different ways to show you how to use them all. But at the end, all this question boils down to is delta P equals F L over D rho V average squared over 2. So the problem is finding F. Any questions about this before I get into it? Okay. So what's the first thing that I should check or do when I'm trying to find F? Calculate the Reynolds number. Very good. So calculating the Reynolds number, as I mentioned on the hand calcs, is the first step because we need to basically determine what equation we're going to use to get F. So one is calculate Reynolds number. For Reynolds number, we need the average velocity. But in this problem, I've only given the volumetric flow rate. So now we have to calculate the average velocity. So NPS schedule 80, sorry, NPS 12. So how the standard pipe sizing works, I posted a link to the Wikipedia page because it's actually really good on this. The NPS kind of gives you an outer diameter, and the schedule here gives you the wall thickness. So this is because it's not just this design of this sort of thing isn't just a fluids problem. You have to make sure your pipe isn't going to burst. So that wall thickness and that NPS 12 is important for determining, say, the maximum pressure you're actually allowed to have in your pipe. But we're just doing fluid stuff right now, so we don't need to worry about that. So the diameter is going to be the outer diameter minus 2 times the wall thickness. So OD is going to come from NPS 12. Wall thickness is from schedule 80. So that's 12.75 inches minus 2 times 0.687 inches, which is 11.376 inches. So I'm going to convert that back to metric because all our other flow quantities are metric. So we're just going to look up the NPS 12 is usually given in imperial units. But the Wikipedia article is really nice because it also gives it in metric directly in the table. So I could have also just read the metric quantities off the table. So anyways, we've got the internal diameter of the pipe. Now, so the average velocity is going to be V dot over A, which is that 0.1. So just volumetric flow rate over the cross-sectional area, which we now have because we know the internal diameter. So average velocity of that. Now the Reynolds number based on diameter is the average D over nu, which is 1.52, 0.289, 1 times 10 to the negative 6. And that's 439,280. Okay, so we checked our Reynolds number. Is this a laminar or a turbulent Reynolds number for an internal pipe flow? Turbulent, right. Remember, for internal flows, we use the criteria based on the internal flow Reynolds number. If you got this Reynolds number for the boundary layer on a flat plate, you might say it hasn't transitioned yet, it's still laminar. But that's not the case for internal flow Reynolds number. Like I said, completely different Reynolds number. So this is definitely turbulent. So now we're going to compute F. Okay. So we need to get epsilon over D, our relative roughness. So in the question we specified that this was steel pipe. The Moody chart is very handy because it gives you relative roughness values for different types of pipes. So see this here, commercial steel. Our relative roughness is going to be 0.045 millimeters. So that's 0.000156. So that's good. We have a Reynolds number based on diameter and relative roughness. So what calculation method did I recommend for hand calcs, which is what we're doing right now, for a turbulent case? Holland equation, right? So let's use that. 1 over square root f, negative 1.8 log 10, 6.9 over Reynolds number, plus the relative roughness over 3.7. Okay, our relative roughness is 0.000156. Again, that's 1 over the square root f. So our f is 0.0150. Any questions on that? So that's the method for the exam. And I'll be clear in the question that I want you to do this method for the exam. So let's do the Moody chart now. So this is how you could say check your work on an exam. Okay. So we know we're going to be in the turbulent flow regime. So the bottom axis of the Moody chart is the Reynolds number based on diameter. So we were at 439,000. So we go and find that on here. Let's round that up to say 450,000. So that's going to be this line here. Okay. So we go down to our Reynolds number. We pick 450,000, which is this line. Now these blue lines that go like this, these are lines for different relative roughness values. So what you do is you go to your right-hand side axis, you find your relative roughness, and then you follow that back to hit your Reynolds number line. So our relative roughness was 0.000156. So 0.000156, that would be like here-ish. So you might notice like we only have lines for 0.0002 and 0.0001. This is why I think it's better we just use the equation, because we're kind of going to be halfway between that. So anyways, we follow those lines back up. Let's say round up to 0.0002, and we follow this blue line here. And this intersection, we now go to the left-hand axis, which is our friction factor. We get 0.015, which is roughly what we got with the Holland equation. So this lovely chart is just a way you can check your work on an exam, but again, the Holland equation is much easier. Are there any questions on using the Moody chart? So again, you can also look up if you computed your Reynolds number. Like this chart was also made when, say, 64 of the Reynolds number might have to be something you did by hand. Like you might not even, or like with a slide rule or something like that. So that's why they give the laminar flow as well, 64 over the Reynolds number on this chart, because you can just look up for laminar flow your Reynolds number there. There's also some interesting things you can point out. So when you have extremely rough pipe, the friction factor kind of levels off. You don't really see the drop that you get with smooth pipe. There also is a limiting case here of smooth pipes, which is when you have zero relative roughness, and that's this kind of bottom line. It's very hard to read, but this is like almost very smooth. It's very slightly different lines. So you'll notice in that friction factor equation, again, this is just an approximation of the Colebrook equation. If we go up to the Colebrook equation, you still get some friction factor when your relative roughness is 0. Okay, so that's how we read the Moody chart. So I won't go through the hand-by-hand iterations of the Colebrook equation, but I'm asking you to do that on the homework assignment that you should do to prepare for this week's tutorial. I won't ask you to do that by hand on this tutorial, but it's good so that you can sort of do that in a spreadsheet once you've done it by hand for a couple iterations. Okay, so now we have our friction factor. Let's compute the pressure drop, FL over D, rho V average squared over 2. So that's 0.01. What did I say? So again, I'm going to use the Holland equation values, 0.0150. L in the question was 30 meters over the diameter, which is 0.289. Dealing with water, so 1,000. So our pressure drop in this NPS 12 is like 12-inch pipe. So like roughly a foot in diameter that we're talking about. So our pressure drop here is 1799 pascals. So that's like 1.8 kilopascals. So again, for any company or in any engineering application where you have to transport liquids or gases long distances, the frictional losses just due to the sheer length of the pipe is the main cost for those companies. So I have also posted an example on Learn of how to use the Colebrook equation for iterations. So I posted a spreadsheet version here. So you can look up what's actually going on here. You can spend some time on Learn, but you take an initial guess and then you keep iterating down. So with the Colebrook equation for this, we've got 0.0152. Again, with the Holland equation, we got 0.015. So close enough for hand calculations. So that's posted on Learn. I'd recommend going through that because in your tutorial this Thursday, the friction factor calculation is definitely a little complicated, but it's not really the key concept here. The key concept is about major losses in pipes. So for example, for a fixed volumetric flow rate, when your diameter changes, everything changes because your Reynolds number changes, your friction factor changes, so the pressure drop changes. There's a lot of different effects there. So in the tutorial on Thursday, we're going to explore the effect of these different variables. So it's good just to have a base knowledge of how to calculate the friction factor. So that's a 10 iteration spreadsheet you can look at. I also posted a little Python example. So if you want to do an equivalent one in MATLAB and have that ready for the tutorial on Thursday, that'd be useful. So you can see the bottom, we get the same answer from the spreadsheet, 0.0152. So this is more in line with what the algorithm that I gave you for calculating the Colebrook equation. So you start with epsilon, D, your Reynolds number, and an F initial guess. You do the right-hand side here. So the right-hand side is that big log thing there. Then you get your friction factor by 1 over the right-hand side squared. And that friction factor is then your F when you do the right-hand side. So you just iterate this. It's very quick, and it converges quite quickly by hand. Oftentimes, students are made to do that by hand on an exam, but I'm not going to make you do that by hand on the exam because I just think it's just pure calculator error that you'll start accumulating, and then like it won't converge, and there's just a whole bunch of other issues that will happen. So, are there any questions about this, what I've covered so far? Because I'm just going to kind of review this for the rest of the lecture. Yep. Right. Yeah. So pressure is always relative in piping systems. and in incompressible flows in general. So it doesn't matter if you have a super, super high pressure, the pressure drop is the same regardless of what P1 is, for example. Okay. Yep.
How does elbows, T's affect this?
Very good questions. Elbows, T's, that sort of thing. You'll notice those aren't in this equation, so we're doing that on Wednesday. Those are called minor losses. So the piping system is kind of made out of different, you could think of them as Lego bricks. You have your long pipe, then a valve, then a long pipe, then a bend. So those are different Lego bricks, and we're going to learn about how to calculate the pressure drop for each of those components, and then combine that all together to do a system analysis. So I'm going to do a quick review on Menti, just of the stuff in this lecture. So please join up here and submit your answers. So the question is, for a Reynolds number of 10, which methods can be used to find the friction factor? It should allow you to select multiple. So this is can be used, not recommended to use. Okay. So, oh, see, that's a good one. So the Colebrook equation and the Holland equation actually can't be used for a Reynolds number. This is, okay, first of all, this is a laminar Reynolds number. So the friction factor is 64 over the Reynolds number. That's on our Moody chart, and it's also, you could just do 64 of the Reynolds number in a modern day calculator. Hopefully your calculator will allow you to do that. The Colebrook equation and Holland equation aren't for laminar flows. Those are only for turbulent flows. So they won't give you the correct answer for a laminar flow. Any questions on that? So what about for a Reynolds number of 100,000? Okay, very good. I think you guys got that. So don't do 64 over the Reynolds number for your project. Use the Colebrook equation. That's the expectation. What about Reynolds number of 3,000? So Reynolds number of 3,000, I think it looks like a lot of people got this. Reynolds number of 3,000 is a transitional Reynolds number, and I haven't given you any methods to do that. And I don't want to, and I know you don't want to do that. So we're not going to be asked to do a friction factor for a transitional Reynolds number in this class. So none of these methods are applicable for transitional Reynolds numbers. So give me your opinion now, kind of, on a plot of effort versus accuracy of these different friction factor calculation methods. I haven't actually tried this before, so I think these points are going to be the average of our 10 submissions. Yeah, so I think very nice. I would say that the accuracy of the 64 of the Reynolds number, it's like an exact, it's an analytically derived, I didn't analytically derive it, but someone did. The 64 of the Reynolds number is exact and it's super easy, so I would put it right at the top. The Colebrook equation is probably takes the most effort, but it's also super accurate, so I would put it there. The Holland equation is only 2% off the Colebrook equation, but it's a lot less effort, so I put it about where you guys have it. Good enough for hand calculations, but 2% error over a pipeline that's thousands of kilometers long can actually make quite a difference. So that's why that wouldn't be used for that case. And two, the Moody chart, it takes a decent amount of effort, as you saw, and you don't really get that much accuracy because you have to interpolate all these different things. So yeah, I'd agree with most of these, except for the laminar case, it's exact. What about my recommendations this lecture on what we're going to use? Okay, so this is for calculating F by hand at a Reynolds number of 100,000. So that's a fully turbulent Reynolds number. So again, we can't use the 64 of a Reynolds number for a fully turbulent case. That's only for laminar. I recommended Holland equation, but I said you could check with the Moody chart. So I'd say most of you got that. yeah, I think we're out of time, so I don't have time to do this question. But if you guys have any questions, please let me know after.